Good morning, everyone. Welcome to this session of Introduction of High-Speed Serdes. My name is Koushik 𝗧𝗧. I am from Cadence, Hyderabad. Today, I think this is my second session where in the previous session I talked about analog design, I think introduction to analog IC design, and in this session I will be continuing my discussion with respect to high-speed interfaces or Serdes design. Now, whatever I will be telling today or whatever I will be showing is mainly targeted for educational purposes. Nothing is that I will be showing is coming from either or Cadence or any other company's intellectual property or confidential information. It's only on my own personal basis that I'll be showing today. So thanks to everyone for joining this call. So this session is targeted for mainly students who are currently graduate or postgraduate and pursuing projects or pursuing research in VLSI domain. So VLSI as a whole, right, is a vast domain. And when we talked about analog design, the last session I mentioned what is analog design, how analog design is important in our, how it is kind of like associated with our day-to-day life, what kind of study that we have to do in order to get a career in analog design. And here also in this particular session I will be talking in terms of the not exactly analog design, but it's again a very vast topic. Let's say when you talk about high-speed interface, I will talk about here what exactly is this high-speed interface means and how this high-speed interface, specifically there is a term called Serdes. I will take you through what exactly the Serdes is, and then from there I will also share my understanding or my kind of vision in terms of creating a career or taking this particular domain as a career objective or career growth perspective, right? I'll show how much growth is there in this particular domain and specifically on this high-speed interface designs. So with this, let's get started. I think yeah, so when I talked last time, even in the previous session, I said, okay, where the analog design is associated with our day-to-day life. And I also talked some applications in analog designs that time. And there I mentioned that, okay, data communication or high-speed data communication is one of the field where we generally use our analog design concepts also. Now, today, if you look at it, we are at a kind of like a we are at a life where we handle or deal with or getting surrounded with several data every time, right? Since morning to since we wake up, open our eyes, and even when we are going to sleep. The entire duration we are handling multiple data, high data transfer, right? And then there are some other advanced categories where we are nowadays exposed to. Let's say another thing is kind of like we say neuromorphic computing, or we say it as a quantum computing. So these are again emerging field, or already we are into it, right? Where we talked about huge set of data. Mainly there is a term that we generally use every now and then is artificial intelligence, right? And there also we actually are exposed to huge amount of data, and that data needs to be transferred from one device to another device, or one medium through a medium, right? From one side to another side through a medium. So that's huge data transfer, data requirement is there, and that we can do. I mean, for that we need a kind of like, high speed, medium high speed protocol, high speed, support through which we can transfer the data from one side to another side. So now this term called Serdes is that particular technique or technology through which we can do it, and that it can make it possible, right? So if you, in this particular place, if you look at this diagram, the diagram is kind of like a conceptual view, conceptual visibility, where we look at, I mean, it's a kind of like a galaxy of data. You can look at it, the dense data transfer. I mean, it's always there. I mean, we are surrounded by this, but we never can visualize this, right? It's beyond our visibility, but data transfer is always there, and high speed data is always going on. Now we have data. Right now we talked about our disk, I mean our memory, devices memory, right? When we talked about our mobile phones, like gigabytes memories, and that is going from gigabytes to terabytes and then from zettabytes. So now this is like huge volumetric data that we have nowadays. We have data available across multiple places, and we need to transfer using cables, wires, interfaces. Now this data, right, is there, and you need to transfer the data through multiple mediums, and these mediums are basically can be a physical medium, right? It can be a wireless medium, it can be an optical medium. So there are multiple mediums through which we transfer the data, and then once we transfer the data, we transfer it in a multiple speed, right? And what it's happening is, when we are transferring in multiple speed, that medium needs to support the speed, and we will see what kind of effect that we can see in that medium, right? And again, if I look at it from the point of view of, let's say, interface, right? As I said, medium and interface, right? There are several protocols that we generally we talked every now and then, and these protocols, if you look at currently in what I am trying to share here, is very much high level understanding of these interface protocols. Now what is protocol, right? So if you look at protocols, there we are talking about protocols. Protocols is nothing but a kind of rule or regulation, or let's say when an army of soldiers goes, right, I mean, they have a protocol that they follow, or everywhere we follow, I mean, in a kind of like a structured manner. When we talked about, right, there are protocol in our work area, there are protocol in our personal life, there are protocol. Knowingly, unknowingly, we have to follow the protocols to make a better, a better outcome or better efficiency. So here also, when we do data transfer, we follow a protocol, and this protocol has been derived through some consortium body, right? And they derive what kind of protocol, what particular case or application or media can use, right? So that's how the protocols have been evaluated. First have been introduced, and then these protocols are going from generation to generation, right? From initial generation, the protocol started maybe for a lower speed, and then as we move, right, that protocol remains, the name remains same, but generations are getting improved from or advanced from one generation to another generation. So if you look at it, there are several protocols, and sometimes we take some name for some specific application. Now I2C and SPI, as it's shown here, right, these are basically used for device to device wired communication purpose. Let's say when the data is transferring from into a, let's say you have a sensor network, right? There are several sensors placed maybe in a kind of like, in an agricultural field. You have sensors placed in multiple locations in that field, right? And then you want to measure the physical quantity through the sensors. Maybe that there can be how much water is there in that particular cultivation area, right, in that particular area, and then you want to, and all the sensors are placed in that particular overall the cultivation area or the agricultural lands, right? Now this communication between all those sensors, and then finally coming the information into a kind of a central location, and then controlling the water content or water flow into that overall agriculture field, right? It's getting done using a controlled sensor network, right? And those kind of cases generally you can use SPI, I2C, or any other kind of interface. Now SPI is again kind of a little bit high speed interface. You see there are RS-332. RS-332 is generally we see in our computers or the CPU's backside that there are some kind of, you can see there are some kind of ports, and those ports are having some pins on those ports. Those are called RS-232 port protocol. I mean, through that port, whatever data transfer is happening, that is following this RS-232. USB is again, we know about USB, we talk about it, USB ports in multiple devices. Then PCIe is a peripheral component interface express protocol. This is used in our let's say motherboard, where we have the processor and the and there are some kind of let's say display the video processor versus the maybe some other components inside the computer. There are that's PCIe is used. Ethernet is another one. Ethernet we generally use for internet. Let's say when we have our Wi-Fi connections, we have the internet connectivity from one device to another device. We use this protocol called Ethernet. Now if you look at it, and obviously there is memory bus, like memory for memory transfer, like DDR and then LPDDR, double rate. Actually this is like basically LPDDR is like again a low power version of the DDR. Then GDDR is graphics DDR. So this is basically for memory data transfer, where a large set of data is getting transferred from the memory to the processor, and then doing the required activity. Storage, eMMC, SATA, they are used for storage. Cable media, through the cable media, whatever the data is transferred, getting transferred using the USB and HDMI. We know about HDMI. It's generally if you can currently in all these televisions at the backside, we see HDMI cable, and that cable we use and connect it to another device, maybe where we use the set-top boxes and all, right. Through that the display content will come and in a very high definition quality. So high definition is again like you have a huge amount of data, and then when you transfer the data, right, you need to make sure that data transfers properly. There is no as such any issues in terms of data contamination or data loss, right. So that's why I mean all these interface protocols are used in multiple applications. So then what kind of I mean all this interface talks about. I will in the next slides I will share some of these ideas about what is that interface protocols, right. But again, if you look at this particular side right here, computer I/O, this is basically PCIe, and here I have mentioned Gen 1 to Gen 6. Now this is basically these speeds, right. Gen 1 to Gen 6 basically it talks about multiple speed. When we see speed, we talk about Gbps, like gigabits per second data transfer per I mean 1 second it's like 10 to the power 9 single data is getting transferred. 10 to the power 9 it's like 1 million 10 to the power 9 could be 100 million. Yeah, I think that's the thing. So that much of data throughput is going. Now from generation to generation, although the protocol remains PCIe, but it's changing in terms of how the data is getting transferred, right. How fast we can transfer the data using the same media, right. And maybe the media is also changing from generation to generation. It is becoming much more challenging there. So we are trying to make sure that through that medium we are actually sending more and more data without having any data loss or data contamination, right. And that's how these generations are mentioned here. Ethernet also, there are several standard naming conventions here, like 10G base X, 10G base T, 10G base CX, and everything. Now all those things, right, are driven by driven by the media. There are several factors associated with all these namings, right? Like 10G means 10 gigasamples. Base is a media, and then there are some other terminologies, X, Y, and all those names. I think I may not be able to recollect every naming today, but the overall concept is, right, if someone wants to know, I mean, definitely you can have some more detailed study, but the main concept here is it is like a Ethernet protocol, and that particular Ethernet protocol, through that protocol the data is getting transferred from one side to another side, and this specific application is for internet that we use. Okay, so that's the main idea. Now, although I mean it looks to all of us that it's a really huge amount of variations like versions. I mean, here I may have added quickly something that came to my mind, but even there are much more. There are many other serial interface protocols that are getting used. Maybe there, and please don't go by these numbers. These numbers may not be exactly the one that we use in the industry, but I'm just trying to give you a kind of an idea that how these numbers moves from one generation to another generation. Okay, so if someone wants to have a detailed understanding, please feel free to go through. There are several component materials available in the internet, so and we can look at it. But the bottom line here is, right, all these protocols, right, all this interface, actually we call it as serial interface. Now, why it is serial, why we use this term as serial, I will quickly come to it. But again, everything, wherever the data transfer is happening, right, everywhere there is a data coming in one device and the other device. Now, this data, as I mentioned in the past, and you have an understanding, okay, what kind of data it is. It's a kind of a digital data, right, that is getting transferred. Now, once the data comes to this device, the data is getting converted into an analog processing mode, and then it is getting, whatever the contamination happened, right, we do some kind of processing here to make sure that to take this noise part out. Now, again, what is noise, what is signal? Again, that's where we talked about in the past. Now, we will also share some of these ideas like SNR, and then bit error rate, and then all those terminologies when we do this interface or when we do the data transfer, right? So once the data is there in this source device, we actually transmit to the receiver through a media, right? And whatever this transfer is happening, this transfer can happen in a parallel way, or this transfer can happen in a serial way also. So there are some advantages and disadvantages for parallel to serial kind of stuff. I will try to give something, but overall the idea here is whenever all these protocols are there, the data is getting transferred from one to the other side, and there is a component called Serdes, and within this transfer, and that Serdes component or that Serdes nomenclature is common. There is no as such any change. It's always like wherever we see data transfer, Serdes is there, right? I mean, that concept is coming. Now, from that concept, like for analog designers, right, how that Serdes that concept is connected, right? From an analog design perspective, from a career development perspective is where I'm going to give that understanding. Okay, so let's talk about high speed, right? We say that this session is on high speed serial interface. Let's talk about high speed. What does it mean by high speed? Okay, I think there is a display problem here. This is basically speed. This guy is showing a speed here. It's in black. Now, what I am showing here is it's basically year to year. Like, I mean, as we move from 2010 to 2020 and 2030, how the speed, data speed is actually varying. It starts from 1 gigahertz. Then around 2010, when we were there, we were talking about data transfer of 1 gigabits per second. Now 2020 we moved, and we actually have seen multiple applications that talks about 10 gigabits per second, right? And then from 2020 to 2025 and 2030, we are talking now around 100 gigabits per second and more, right? So when we are moving our speed from decades to decades, years to years, right? What exactly is the main challenge? The main challenge comes like, this is basically a demonstration of the challenge. Like first, when we talk about 1 Gbps, we have to sample the data, right? We have some additional time here, I mean, for sampling the data. But when we go to the 10 Gbps, the time has been reduced by that ratio, right? 10 times. I mean, it's much more limited, right? In this particular time, we need to make sure the data is properly sampled and processed to the next stage, which is basically a challenging factor, right? Again, once we move from 10 to 100, as likely you can understand that this is even much more challenging, right? From this time to this time, we have even very much constrained time period. So earlier we were having enough time, and in this enough time we can do whatever we want, what kind of processing we want, right? But now this particular time is reduced by, let's say, 100 times, right? So in this process also we have to do the same kind of processing what we used to do here. Otherwise we may not be able to reproduce or may not be able to transfer the data properly from that we used to do in the past, right? So there will be there will be loss of data here, so that the efficiency will not be much. Again, the other part here is, right, when we are transferring data at a lower speed during 2010, right, the power, the system power it used to take was pretty less, right, compared to what we have to do today. Today, if we have to transfer the entire data in a smaller duration and do the same processing we used to do earlier, we definitely have to increase a lot of power. But again, if you look at it, it's actually contradicts with respect to our current need, right? We are talking about cost effective, we are talking about applications or our devices to last longer and our devices to give more power backup, right? We will just charge for one time and it will last forever, right? For, let's say, more time, not forever though, but let's say I don't want to charge my device every now and then, right? So but if you look at the data transfer, right, I mean, we are now looking for higher data transfer, HD content transfer, and we want to see everything in a large volume, right? We want to enjoy the transmission in a better way. Then we definitely have to make sure that we are doing the processing with the less time as well as with again reduced power, right? Forget about maintaining the same power. We are mainly talking about even reduction in power. So there is a terminology that we talk about every time is like the figure of merit. Figure of merit in this particular interface design, when we talk about picojoule per bit. Now picojoule is a kind of an energy energy measure. Now how much power we consume, right, to transfer 1 bit, right, is a kind of like a figure of merit for our design. Now this particular number, as we go from one generation to another generation, as speed increases, right, we are making sure that this particular number is also going down, right? So if you look at today, right, there are PCIe, as I said, peripheral component interface. There are PCIe, when we talk about right now 112 gigabits per second PCIe Gen 6, and there are some numbers of, if you look at some of the research material or some of the latest IEEE publications material, you can see that the number is around 20-25 picojoule, and even some other publications where people are doing more research and trying to reduce the number, right, they are quoting around 10, 12, such kind of numbers like picojoule per bits, right? So this is where the attention is going, right? I want to make sure my bit error rate is excellent. I don't want to get my data lost in between when I'm going for higher data transfer. At the same time, I'm maintaining or making sure that my power consumption, my battery doesn't dry so fast. I need to make sure my battery maintains its power for a longer duration. So that's how this kind of like design challenges are there, right? So I will talk about it in some more details, but I'll gradually go there. Okay, so as I so far I mentioned, I talked about, I mean, what is an interface, what does it mean by high speed, what exactly all these interfaces are going to, a common term called Serdes. I have not mentioned what is Serdes, but now in the next section I will give you a brief introduction of Serdes. I think majority of the folks who have interest towards, let's say, electronics, VLSI may have already come across this term called Serdes, but for a wider audience, right, I would like to give that particular understanding of what exactly is Serdes, right? Remember, this we are talking about physical data transfer in a physical media, right? And that media can be anything, can be like physical media, optical media, or any other media that we see nowadays, right? Or maybe a PCB stress, that where data goes. PCB is printed circuit board. Generally you see it into your devices. If you open up your device, you will see all this PCB sitting, and there are several stresses that you can see. Okay, yeah. So now let's look at this diagram. This is just a representative diagram that talks about that actually take us to the Serdes, right? So parallel link, right? So parallel link, there are, if you look at it, there are parallel data traces shown on a PCB, and all these components are electronics components, like they are maybe some processors, maybe some display units, or some other purpose, like maybe some capacitors are captured, or maybe some transistors, or some audio codecs, or some other applications for this particular case, right? Now if you look at this particular diagram, you can see some parallel lines going, right? And all those parallel lines, because of these parallel lines, right, you need a bigger landscape, right, through and for that bigger landscape you have to develop it for a bigger or higher cost, right? I mean, and then not only just you need to just take these signals, you also need to make sure when you're adding these signals, you need to have shielding across the signals. Otherwise the signals, if it flows in high speed, they will actually disturb each other. They will try to talk to them very frequently, and generally there is a term called crosstalk. So crosstalk is definitely one issue if we have all these things running in parallel. Now if you look at this particular server rack, right, the server rack generally we see in data centers, right, several servers are placed and they are connected at the back side of it, right? And if you look at it, it gives us some kind of initial impression that, oh, what a cluttered way that this is added, right? But I don't think there is a better way to handle this in this particular arrangement. I mean, definitely, although it looks cluttered, it's look complex, it is the thing it is, right? So what we can do to make it much more cost effective, much more easy to handle, much more where you can get the throughput better, right? So that's how, if you look at it, right, from there, if you look at this particular diagram, it gives a kind of like a better impression. Earlier it was cluttered, earlier it was very busy, and now it is much more content, much more clean, right? Both, like the PCB stress, you talk about the PCB stress, or you talk about this server rack, right. So, how it is getting done properly, getting in this way, it's basically coming into a serial manner, right. So, this is basically clean, simple and cost effective, right. So, what is the point here? The point here is, once we have everything in parallel, the data is transferring in parallel. What we have done is, we have taken all the parallel data and then put it into a single line. So, that means we are making the parallel things into serial. So, that is called parallel to serial conversion, right. So, from there we are talking about Serdes. Serdes means like replace all wires with one single wire is what we are talking about Serdes. Here, if you look at this diagram, there are multiple stresses of lines. These lines are actually transferring data from one side to another side, right. So, now one side means like here you have high speed data, again you have high speed data here, again you have high speed data here, and all this data is actually transferred from here to here using the same channel, and the channel is actually instantiated multiple times. Now, this is basically, if you want to do that, it is costly because you have to add multiple channels. At the same time, there are high speed data flowing in these channels, and that will do some kind of crosstalk between these channels, and that crosstalk will impact the bit error rate. It will impact a lot of quality factors. So, this is not the correct way to transfer data for high speed, right. Maybe in the previous earlier, right, when we were having a lower speed data, maybe some up to maybe some few megahertz, these were not that critical in terms of quality of data transfer. Cost were always there, but I am not talking about cost. If the cost is manageable, but still the quality of outcome, right, if you move from megahertz to gigahertz to terahertz, right, definitely this is not at all a solution. So, that is where the Serdes has been introduced long back, right. I mean, this Serdes is not new. This Serdes introduction happened like, let us say, around 90s, 90s, 60s, 70s, 80s time frame. People started introducing Serdes in all these interface data transfer, right. So, when we talk about Serdes, right, it is again the data which are in the parallel form in the transmitting device are getting converted into serial form into the channel, and then from the channel it is going to the other side. Now, how to do that? I mean, this is very easy to say, okay, we are putting it into a single channel and then transferring into the other side and again reproducing in the other side, right. But again, the question here is, if I do it in this fashion, like earlier the data was going independently in a specific speed, right. Now, you are clubbing everything together into this channel. So, that means this channel is actually now having a data which is much higher, which is much higher. The speed of the data is much higher. The throughput of the data is much higher. So, it's basically you are muxing. So, I'm talking about mux and demux, right. So, you are muxing all this data. Mux means getting all the data in a time multiplexed manner, like you have the data going from I mean a larger data, right. I mean higher lower speed data or a lower or a wider dimension data in the time domain, right, and then you club everything together and then put it in the channel. So, that means the channel is actually having a data which is much faster. I will show about it what exactly the challenge there is. So, although we are addressing one challenge here, we are also talking about another challenge here, right. So, in this way we are reducing cost, we are using a single channel, but at the same time we are introducing many other challenges that we have to address to make it happen, right. So, we will talk about those challenges and then we will also see how those challenges we can take care. Okay, so, why Serdes is important? Serdes is important for reduction in number of wires, reduction in crosstalk, simple and cost effective, right. So, this is a very much a well known diagram that I got in the internet and I put it here. Now, if you look at it, right, this data, the color coding is showing how this data in parallel is getting into serial and from serial to parallel again, right. And then again the same thing shown here. It's basically both the diagram are showing the same concept through which we do the serialization and parallelization. So, parallel to serial and again serial to parallel. So, that is how we are talking about it, and then when we are doing all these operations, we have to make sure this data is coming here without an error. It is not like if this 0 is here, it can be 1 here, or it is a 0 is here, it can be 1 here. It is not like that. So, here you have, let us say, a total 10 bits or 8 bits, right. These 8 bits, if it is going around, let us say 1 gigahertz rate, right, this particular channel will actually should be running at 8 gigahertz level, right. So, then we have to look at whether this channel is capable of doing it. If not, then what we have to do, what we have to make sure to address, right. So, that is one thing which we generally take care before and after, right, doing the data transfer, right. So, we know the channel is a kind of a media which is known to us. It is not an unknown thing. We know that its characteristic, we understand how the channel behaves, and accordingly we take some kind of, we do some kind of processing, right, in this range, right, in this particular block, which we do some processing in this block and finally get the data out, right. So, overall guys, if you look at it today, we are talking about data transfer, high speed data transfer, high speed interface, and we have entered into a concept called Serdes, right. Now, this Serdes, right, this is the basically serialization, parallel, serial, parallel. This is the entire concept of Serdes. Now, we will go to gradually we will go to the next sections, and we will see that what are the challenges coming in this particular arrangement, right. How we can basically address those challenges, right. Okay, so here I have given, okay, this is not visible. Here I actually have given the, the 𝗧𝗧 where from I have taken it. So, again, this is as I said, this is pretty much intended for our understanding, educational purpose. Nothing is confidential here. So, this particular diagram, right, we talked about so far what exactly is Serdes, right, and now in this diagram you can suddenly think that, okay, how this diagram is mapped, right. I mean, we have shown some kind of protocols, we have seen some kind of concept called serial to parallel. Now, where this particular diagram is linked, so let me give you some thought process. So, now here we are talking about the Ethernet, right. Remember, I have shown you a protocol called Ethernet. Now, here we are talking about that particular protocol called Ethernet. In that protocol, we see that there are multiple layers like data link, physical layer, and the medium. Now, this medium is the physical or maybe the wireless medium, or maybe the optical medium, or it can be any other medium, right, through which the data transfers. Now, there are some component in it, right, in the physical layer. PCS, physical medium, basically physical coding sublayer, and then PMA talks about the physical medium attachment, and the PMD is physical medium dependent particular layer. So, these three layers constitute the phi layer. Phi means physical layer through which we actually process the data, right. And then the PMA is the serializer and deserializer, right, where we do that operation I just have shown you, right. And then we definitely has a clock recovery there. Clock recovery meaning every data that we process, we need a clock. Without a clock, it is not possible to process any data. We need a reference, right, and that is the clock reference. So, we need a clock. So, but then when we transfer the data, we don't transfer clock, right. So, we need some kind of concept called clock recovery. From the data, we transfer the data, the receiver receives the data, it actually creates a clock from that particular data. So, that is called clock recovery. Now, in this when it is Serdes is connected to this particular level, which is PMA, and then PCS and PMD. So, PCS and PMD, they are basically they are again they are also hardware kind of stuff, but I think they are getting done using the digital way, right? It's like you have either processors, or you have the FPGA and all, right? So then this particular place we will talk about more on this PMA, where we have the circuits. Yeah, I see there is a phone. Please.
Hello.
Hi.
Sir, my name is Veena, sir.
Hi, Veena.
Sir, I have a question.
Yeah, please.
Why is Serdes technology important for high-speed data transfer?
Yeah. Okay. Anything else?
No, nothing.
Okay. No, Serdes, as I said, right, high-speed data transfer. For high-speed data transfer, you can do the transfer using a parallel combination. Let's say you have 10 bits and you transferring the 10 bits, right, from source to destination. You can have it in parallel form, like all the data can go in parallel, but then I have shown you that if you do it in parallel form, there are some challenges. You cannot increase the speed to a level and then finally reproduce the data in the termination, right? So there the concept is coming called Serdes, where you are converting the parallel data into serial form and then transferring the data in the medium in a serial form, right, which is much more cost effective, which is much more manageable, and there are not much impact with respect to multiple noise factors, right, for the parallel arrangement, right, and then it will again go back to parallel. So parallel, serial, parallel, that's why the Serdes is coming, right. So that's why Serdes is very important in high speed data transfer, right. So it's like data transfer is always happening, but you are actually doing the transfer through a kind of like a Serdes arrangement. Okay. Okay, thanks for this question. This is a good question. So some part of it will be answered here as well. So if you look at it, right, basic architecture of Serdes. So first, parallel data in and serial data out, which is serialization, right. So this is the parallel data, and then I am actually making it serialization. Then serial data in and parallel data out. Serial data in this side and parallel data out. So if you look at it, our main intention is whatever data I am getting here needs to be properly reproduced here and without an error, right. And that's how we have to do some of the processing in this part, some of the processing in this part, knowing that we know a known channel, right. Definitely we need to know what is the channel through which we are transferring the data. So knowing the behavior of the channel, we can transfer the data in this way. Like instead of transferring the data like this using 10 different wires or 10 different channels, right, I am using the same channel, I am using a single channel here, and then I am transferring the data from here to here using this concept called Serdes. Now if you look at it, now if you have a data of 1 gigahertz, right, which is 1 nanosecond duration data, that 1 gigahertz data, when it is transferred into this channel, this data will become 10 gigahertz, right. So here the channel needs to support the 10 gigahertz, that must, right. When I am saying support, that means channel, when the data is flowing through the channel, I mean, let's say in that particular duration of 100 picosecond, it will take some time, right. I mean, the energy transfer through the channel, and the channel will have its own resistance. Consider this as a kind of like water flowing through a pipe, right. So as the water goes from this side from the source to the destination, the speed of the water flow will be reduced, right, and that means there is a kind of like a resistance coming from the channel, right. And again, that resistance in this case, right, will again be frequency dependent, right. It's a kind of like the channel is a physical media. It has its capacitive inductance, it has its resistance and all, right. So because of all those components, the channel has its own behavior. So that is known. We know that channel behavior. It's not like we don't know. So knowing the channel behavior, knowing the issue coming from the channel, we need to handle it such a way that the data at the left should be reproduced at the right properly. Okay. Now challenges in design. So let's now talk about challenges in design, right. So when we talked about so far. Let's go back a little bit just to make sure that we are not missing anything. So we have so far seen the speed. What does it mean by speed? What does it mean by parallel interface to serialization? Why we should be doing serialization, and then we slightly or very high level talked about the challenges. Now we will go through these challenges in some more detail, right? And then gradually we'll go to the with the challenges we'll go to the subcomponents of the Serdes, like what are the subcomponents. But again, just to remind or probably just to connect to the audience in a better way. So in this particular session, I will be giving then high level overview of all those concepts, right, and how those concepts are actually going towards in the industry, how we see those concepts, and how this particular domain can be of much interest of the students community, researchers community, and what kind of research that we can do and how we can make it much make this particular domain much more useful for us, right? And again, in the industry also I see there is a requirement of this skill set, right, of like Serdes design. Right now I will take you through that overview, but then for your larger interest, if you want to do further study, there are several documentation, several well documented materials available in the internet, right? So you can definitely go through all of them. There are very good slides, very good presentations, very good audio, video, AV recordings available throughout. But again, the idea here is, right, there is a scope, there is a huge demand, and going forward the demand will continue to be there. So I will share some of them. Okay, let's go through the challenges. Okay, so when we talk about VLSI, we talk about fabrication in silicon, correct? So in the previous discussion, I have shared with you the challenges that is coming in fabrication, silicon fabrication, and then especially in the analog side or maybe some part of the digital side, right? So when we talk about fabrication, we fabricate devices, means transistors. We also fabricate the interconnects, right? Interconnects means the connections from one transistor to another transistor, the data or the signal should flow, right? The electrons should flow, right? So then that particular connection is through some metal routings, right? Now that's called interconnect. Now once we move from one technology to another technology, as we go, the technology shrinks, right? Why technology shrinks? Technology shrinks to accommodate more devices, more functionality, right, into the same landscape, right? So it's now we are talking about 2D to 3D. 3D means, like as we see, like using the same landscape, but again having more and more structures there, more and more accommodation there, right? So that's why we are seeing all multi-storied nowadays, right? So where we have the 3D structures, right? So there also right now we are talking about the 3D structures, right? We are fabricating our devices on silicon using 3D technologies, right? And that's where the challenge is coming. Now as we move on from technology to technology, as we fabricate our devices in silicon, right, our technology, we see that the delay, again, why we are talking about delay? We are talking about delay because we are talking about high speed. Because if the delay is not getting controlled, we cannot achieve high speed, right? Delay, speed versus delay is like delay is 1 upon speed, right? 1 by speed, right? So that's where this delay is coming into the picture. So now as we move from process technology, as this process technology scales down, there is a bottleneck coming with respect to the interconnect delay. Interconnect means, as I said, the interconnect is the connections between one device to another device through some wires, right? These are the wires getting fabricated. There are multiple stacks of metals, right? Metal level 1, level 2, and these levels are connected intermediately using vias. And that's where all these structures are, right? These are global interconnects on the top, and then the local interconnects at the bottom, and then for highly dense structures, right, all these interconnects are coming in, right. And what is happening because of all these interconnects in the lower structure, because of the denseness, right, these interconnect resistive components or the interconnect resistance is also increasing, right. And on top of that, the main problem that we are seeing here is the decoupling, coupling between the one connection, one interconnect to another interconnect, right, overlapping or overlap coupling capacitors, right. These are basically impacting a lot in terms of the overall throughput of the data transfer. So because of this, we need to make sure that we are taking care of this interconnect delay when we are manufacturing the devices on silicon. Now, earlier at the beginning, there were use of aluminum, which was good enough for a speed purpose, right. But now aluminum has been replaced with copper. Copper is much better in terms of interconnect resistivity, and we get higher speed through copper. So now in the fabrication technology, widely used material is copper. Some places we can see use of gold as an interconnect, but that as we all know that gold is precious and it's actually is costly. But the advantage of gold is like applications such as, let's say, space or automotive, where we are talking about corrosion, right, and the high extreme kind of conditions, right, where those cases, generally very limited cases, we use gold as a interconnect material, but widely used material is copper. So when we use copper, we actually deposit copper like dielectric etch, like this is all on a silicon, right. We have dielectric, we have the base, we have dielectric, we deposit copper, and then we clean the copper from the top. This is the steps the through is a manufacturing happened, copper interconnect manufacturing. And then this is basically creating a lot of concern when we proceed, right. So apart from these interconnect challenges, right, the generic challenges that we face here is basically signal integrity, high speed, thermal management. Thermal management is another point here that we also discussed in the past. Okay, when there is a energy transfer happens from one to the other side, right, there is a lot of heat getting generated, right, and once we have heat generated, right, then it actually impacts device performance, right. So in order to avoid device degradation or performance degradation, we need to make sure we go through a thermal management process. Now, thermal management process is nothing, but we need to make sure that if there is some heat getting generated, there are some kind of heat dissipation mechanism by adding some heat sinks and all, but that basically happens for power devices. For high speed also, we make sure that in some cases, right, when the device is under heat, we do some kind of pre-analysis through simulations, right. We check whether it is degraded, the device performance is degraded for longer term. We keep the device in high temperature, 125 C. I mean, the grade of temperature, industry grade, is -40 C to -40 degree centigrade to 125 degree centigrade. So we keep the device under stress, right, at 125 for longer duration. It's basically a machine based simulations we run in our setup, and then we see if it is performing well, right. Those are called our reliability checks or thermal management. Okay, so power efficiency, material constraint, and capability of those devices, whether the devices can support that much of speed, right. So that's called capability. Now, signal challenges in Serdes design, signal integrity issues, right. Remember when we talked about Serdes, we talked about doing some kind of processing in the transmitter, in the receiver, right. So this processing that we do, definitely there are some reason, right, to do that processing. One of the reason is signal integrity. So we need to make sure we are taking care of the signal integrity. this particular diagram, if you can see, there are multiple issues coming, right? Signal with integrated integrity issues, like this is basically coming from multiple coupling. As I said, if there are high speed signals going side by side, there will be crosstalk impact, right? So that's here shown here. That means you have a signal frequency here. This is the base signal frequency, is the base band, and on top of it you have another signal component coming here, right? This signal component is nothing but coming from the high frequency components, high frequency signals following in the channel, right? In the design also. So this basically is causing some kind of distortion in the signal. Here you can see the impedance mismatch, right? Let's say this is your signal which is coming to the channel from the transmitter to the channel, and the channel and transmitter, they are not matched in terms of impedance. So what will happen there will be a kind of like, you know, degradation of the signal amplitude, and that will definitely cause an issue, right? We will not be able to reproduce the signal. On top of this particular signal, there will be some additional noise, right? So those noise will be impacting. Now all those things will always happen, and these components will be much more complex and much more prominent as we go in the higher speed, right? So if you see, that's just a demonstration here where this particular signal is basically improved integrity, right? I mean, here you have the signal integrity issues, but then it is basically improved, and this signal integrity is been improved using some filtering or using some mechanism that is used either in the transmitter side or in the device side. Okay, signal degradation, loss of signal quality, right? And then crosstalk and EMI, electromagnetic interference, right? And then impedance mismatch. So these are the main reason through which we see a lot of signal quality degradation, right? Here you see an oscilloscope, right? When you put it into an oscilloscope, you try to measure the output of your channel. So data is coming here, the data is going through the channel, and then you take that output, or maybe you take the input of the transmitter also to the oscilloscope. You put it into using some kind of wires into the oscilloscope, and you see this kind of continuous disturbing signals, right? So this is nothing but all those components are getting into it, right? But a clean signal should be very much, you know, single frequency signal. Hi.
Sir, good morning, sir.
Morning.
I'm Poonam from Highspeed, sir.
Hi, Poonam.
Sir, I have some doubts, sir.
Sure.
Sir, how does Serdes reduce the complexity and the cost of parallel data transmission?
I'm sorry, your first part was not clear. If you don't mind, can you repeat?
Sir, how does Serdes reduce the complexity?
How does?
And the cost of parallel data transmission.
If I got it properly, you are saying how Serdes reduce complexity and
Yes, sir.
Okay, how Serdes reduce complexity and cost, right?
Yes.
Yeah, I think yeah, that's a good question. Thank you. So Serdes definitely helps us to reduce cost, because once we do a parallel data transfer, right? As I said, you need, let's say there are 10 bits data transfer. If it is 2 bits, right, the cost may not be that effective. But if it is more, right, 10 bits or maybe more than 10 bits data transfer, right? So you need 10 parallel channel, right? So in that case, you have to lay down those 10 parallel channels in your PCB or in your system, right? Which definitely takes a bigger area, right? A bigger landscape of the PCB. And again, if the data rate is more, right, you have to definitely make sure that you take care of all those effect of crosstalk, right? You need to space those tracks a bit wider, right? Otherwise these tracks, right, which are parallel will talk to each other in more frequently. Now if you space it out, again you need to make sure you are keeping that keeping a bigger area in your PCB, which means your end product or your end application will be bigger. Now we are talking about miniaturization, right? We are talking about everything coming to a single place, right? We are, as we move on, that's the main idea, right? So earlier, you remember, we used to use USB 3.0, I mean earlier USB 2 and all, where your USB port used to be this big, right? Now we have a smaller port, right, for USB, and there also and that's advanced version of it, right? So what is happening here, we are actually earlier the cost of this USB this particular USB cables were higher, but now as we move on, we see that the cost of these USB communication channels, right, and the USB devices, they are getting reduced. So how it is getting reduced? By using those Serdes only, right? Whereas so that's the concept basically. So you can get much more better cost when you come from parallel to serial. Okay, I hope that addressed your question, Poonam. Moving forward, so challenges in Serdes power consumption. So I think I talked about this part a bit and in earlier slides, where we talked about the picojoule per bits, right? So that's again, power consumption is always there. I mean, as we move on the speed, we need more power to perform the same operation in the same time duration. Okay, so definitely increased switching loss, higher frequency means more power consumption, dynamic power dissipation, faster transition results in higher energy, thermal management, right? So so this is another challenge, as I said, that okay, once you do a processing in high speed, you need to make sure that you are actually consuming more power to obtain that high speed. But again, our end product or our end application does not want it, right? It's not, definitely if you do in this way, no one will take your solution, because it takes more battery, it drains the battery faster. So you have to, although you are working in a high speed domain, high speed application, you need to make sure your design is structured such a way that your overall power is lowered, right? It's getting down. There are some techniques to handle this, but you know, as you move from one technology to another technology, as you move from higher technology to lower technology, this is become more dominant, right? Because once you, as I have shown you, right, the interconnect, right? The interconnect will have a lot of additional, you know, capacitance and inductance, right, which are the parasitics, right? So those parasitics, capacitance and inductance will always be there, and in order to transfer the energy in a high speed, those capacitance and capacitance will need some extra charge, so you have to consume that charge. But there are some circuit techniques, there are multiple research going on that line to handle this particular issue. Okay. Clock data recovery challenges. This is another problem here, because right now what I have shown you is we are only transferring data, right? One side you have a system which is called transmitter. Transmitter means you are taking the parallel data, making it in serial, and in order to do that you need a clock, right? So with respect to a clock, you use that clock and then do that parallel to serial conversion, right? Now this clock, right, it's a kind of like, you know, it's not going as a separate clock to the other side, right? The channel only takes the data. Now how to get that particular clock, and without that clock, again in the receiver end, it is very hard for you, or it is quite impossible for you to generate the same pattern, right, in a pretty much synchronous way. There cannot be much latency, there cannot be much you know, issues. Yeah, so this particular clock, right, you need to generate at the receiver and make sure that the clock phases, right, are in sync with the data. Right now there are some requirements for these clocks, right? Clock jitters, right, requirement in the transmitter, jitter requirement in the receiver. So all those challenges are coming in place. So generally, you know, in the transmitter we use a concept called PLL. PLL is the phase lock loop to create this clock, right? Again, in the receiver we use CDR, clock data recovery, kind of like an arrangement there. So again, that's a analog and digital combination of circuits, right, that we generally design, and there is a huge challenge there. I mean, as we move from from lower speed to higher speed, right now, if we are looking at 112 gig or 112 or 224 gig Serdes, right, 224 PCI Gen 6, Gen 6, 7 kind of Serdes, right, there we need to create that data. From the data we have to create the clock. So there are very stringent, very tight requirement of clock and its jitter components, right. Now we are talking about signals or data in picoseconds, right. Earlier it was nanoseconds, now it is like less than 1 picoseconds, right. So within that less than 1 picosecond, you have additional components called interconnect, right. So you have to take care of interconnect delays, interconnect coupling factors, and then you have to take care of the other factor called the noise coupling from supply, noise coupling from the multiple other sources, right. And then you have to make sure you reproduce the clock properly at the right side, or at the transmitter or receiver side. Okay, so these are the challenges, right, that we are seeing. Design, simulation and testing. So there are challenges related to simulation and testing. We do signal integrity analysis, jitter and noise measurement, bit error rate estimation, eye mask compliance. Now within the during the design cycle, we actually make sure that we have all this testing incorporated, which is like BIST, built-in self-test. This is a very generic term. I mean, generally this is there since longer. We do incorporate BIST pattern, built-in self-test pattern into the design, and check the after the production or after manufacturing how the design has come up with respect to the design throughput. EMI, electromagnetic interference, right. We use eye diagram to measure the signal quality. We use FPGA to do some kind of prototyping of the phi. We do signal integrity analysis. When we do signal integrity analysis in our design, we make sure that we take care of some of the coupling constraints. We cover. We model the coupling constraints properly from PCB, from the packaging, right. So those are the so again, let me try to give you some understanding in terms of packaging, right. So when we have the device in a PCB or somewhere, it is encapsulated in a package, right. It's not a bare die. So die is getting the signal pads, right, the signal bumps, right. We call it as bumps, right. So the signal bump, the power bumps are getting actually connected to the package bump. So now in this case there are some kind of connections happening, and these connections should be very much that's what the material availability makes sense, right. What kind of material is used, what is the length of that bump, right. It depends on the package type. There are several package type. It's like a normal package or a flip chip package, meaning the die is there and the package just come and then attach, getting touched, right. So it's like a flip chip package or a normal package, right, where you have a wired connection from the die bump to the package bump, right. So this particular additional components, right, will have its additional impedance, right. It's like inductance, capacitance, all those factors are coming. Now for high speed, these factors are like much more critical. Low speed, we don't care much, because anyway load speed cap is off, inductor is shorted and all those stuff. But then the high speed, we have a huge amount of impedance coming for this, and that will attenuate the signal when the signal is moving from the die to the pad. Okay. Built-in self-test, generally we incorporate built-in self-test kind of pattern, and then this is the circuit under test, BIST controller, pattern generator. We add those pattern to the circuit, and the circuit will provide something, some outcome, and this outcome will go to the signal analyzer, and we will see whether the circuit, internal circuits, the patterns are properly taken care. That means the circuit health is good here, right? Eye diagram is another way, right? So for signal integrity, we would like to see how what is the health of this eye, right? What is an eye? I mean, you can look at multiple such eye diagrams, but the eye diagrams talks about the health of the media, right? Let's say, when the data is getting transferred from transmitter to the receiver through the media, the signal has to go, the signal energy has to transfer properly. There should be pretty much good matching, and then the other factors, right, that will be incorporated. All those signal integrity factors I have shown. So by looking at, I mean, because of all those factors together, we want to see what is the quality of that particular signal at the transmitter, at the end of the receiver, at the input of the receiver, and the output of the receiver. So what we do, we continuously provide a signal and then try to measure its like reflection pattern also. So that means there is a signal here, there is a signal here, and then this signal interacts in some points, and then there is an eye opening here, an eye amplitude, and eye height, and eye length, right, width. So overall, this width, length, height, and amplitude, right, it gives us a kind of like an understanding of the attenuation issues, the signal integrity issues. If the eye is open, that means it's good actually. An open eye diagram in Serdes signifies minimal signal degradation and high data integrity, right? The right side image is actually an eye image for an advanced Serdes. This is a kind of like non-return to zero NRZ Serdes. There may be the higher, the initial, or maybe the not that I mean the PCI maybe Gen 3, 4 based kind of Serdes, or maybe USB Serdes kind of eye diagram. But the right side we talk about PAM4 based, right? We'll come to that in a short while. Okay, but just to make sure, it's a quick time check. I think we are only having another 45 minutes. So quickly take you through this and then go to the other section faster. So open your eyes to see a better world. So this is a tagline here. Key components. So key components, as we know here, that we generally do parallel data to serial data to parallel. So what are the key components? Obviously we need a serializer and then a transmitter. Now the transmitter, as I said, right, in order for the energy to transfer properly through the channel, there is no attenuation. We need to make sure that there is an impedance matching here. Now the channel impedance, and it's basically 50 ohm channel that we need to make sure that the impedance is matched here, like the transmitter impedance is also matched with the channel. Now on the other side we have a RX. Now this RX is the receiver end. Now once there are some internal component of RX, meaning once the data is coming here, that data needs to be properly, you know, transferred. The energy needs to be properly transferred to the RX, and there will be some kind of contamination here, you know, in this channel. We need to, you know, repair that particular data. So there are some other blocks in this RX, and then finally from the RX, once we amplitude the data, we will put it into a digital deserializer. Serializer, deserializer are of the, I mean, kind of like a digital kind of circuits, whereas TX and RX are analog kind of circuits, where we do the processing more linear way, right? And there is a reference clock. Definitely we need a reference clock to do these parallel to serial combinations, and that reference clock is going through the PLL, where that output is actually transfer to the TX and the serializer. Now the clock is not propagating from here to here, so we need a CDR to regenerate the clock from the data, and that's how this is coming. The RX output is coming to the CDR. There is a feedback, and then that is again going to the RX, right? And then the output of this CDR is going to the deserializer. Okay, so that's continuous, you know, adaptive feedback through which the phase of the data and clock is getting aligned, and as soon as they are aligned, it is locked. Okay. So again, key components, it's like feed forward equalizer, challenge design, like we need a kind of like a feed forward equalizer in the TX just to make sure that we are taking care of the loss in the channel, right. So again, then this one is input channel full swing and there is no noise, that's what it is. Now with this particular noise addition and the channel degradation, we see that there will be a kind of like, you know, obviously this particular signal, there are a lot of noise injected and there is a distortion in the signal, right. If you look at it, this one will never become one, it will be a lot of noise here. Again, this is double one is there, but again it is not fully double one. It's very difficult for you to recognize whether it's 1 or something else, right. So it's very difficult once you have all those channel attenuation, all the other components, right, loss in channel amplitude, right, channel noise and everything will come, and finally you have to get this output, right. There's a phone, yeah. Yes, I can.
Yes. So my question is,
Venkatesh, your voice is not clear.
yeah, now sir.
Yeah, please try.
Yeah, okay. My question is how to build a self-test BIST technique in helping validating the Serdes performance.
How to build BIST technique to?
Yes, help in validating the Serdes performance.
Serdes performance.
Yes, sir.
Okay, so you want a BIST that will give you performance, like how the Serdes is performing, right? As per my knowledge, I think I still have to go back and look at it, but BIST is basically used to give you an understanding not of the overall performance parameter, but will give you some kind of critical. Let's say you want to check how is your a synchronizer working, right? So you can check that part. Maybe there are some techniques through which you can understand Serdes effectiveness, right? But I think today I do not have something to share with you. Maybe I can look at it. But as of the BIST technique is to understand, okay, how much is your the patterns are getting generated. It will give you some kind of, definitely some kind of idea about the effectiveness of or the quality, but there will be some kind of BIST techniques also. There are several BIST techniques, but right now I do not have anything to share with you. Okay, I can check and then look at it. Whether any BIST is there that can give you any Serdes effectiveness, right? There will be definitely something, but we need to check that. Okay, so key components of a Serdes system, like as I said, there are input latch, encoder, parallel to serial, differential, like here the differential driver, right? So differential driver is like the output is differential here. It is a single data, it can be a CMOS data, input latch, encoder, all of this data, all of these blocks are working on a PLL. Now PLL is again analog, maybe some PLLs are fractional PLL, right, depending on the input clock and the clock requirement for this TX driver, right. Generally this PLLs is derived. There are multiple PLLs also depending on multiple requirement like 𝗧𝗧 VLL or 𝗧𝗧 PLL and all those stuff. So there is a bigger requirement of PLL, right. So and it's very critical. Encoder, parallel to serial, all of these are happening with respect to this clock and then the driver. Now this driver can be a voltage mode driver or current mode driver, right? Depending on the application, there are multiple ways to look at this driver. Now there can be again a differential driver or single-ended driver. For all these advanced Serdes, we generally derive a differential driver and then inject the signal into the cable, right, into the media. which is differential non-return 0 NRZ signal, right. So now this one, the driver is again kind of like an analog driver, and we have multiple programmability in terms of driver impedance matching, right. So you can have some kind of additional bits and then program that bits as you want for your design, and that programming happens generally at the initial product testing. Okay, so then the cable, and then finally from the cable the differential receiver and the clock data recovery. Obviously the clock data recovery is must, because you need to make sure that you are doing a parallel serial to parallel combination using that clock, and then you have some decoder logic here, the data output, right. So that data is now again parallel data. If you have 10-bit data here, again you are coming that 10-bit data here, and then you have a RC clock that is needed for the system. Serializer, yes, is one component is serializer. In this component we have serialization, like all this data into a serial data, and then there are some there are different way to do the serialization using even and odd kind of arrangement, right, and you definitely have a bit clock to do that, and this is your overall serial data. Now if you look at it, there is a kind of like latency from the data here to the final data here, right. So that latency we need to make sure that we are calculating, and we are covering that latency when we are sending the data into the channel to the receiver. Okay. Deserializer is the part generally we use in the receiver. Now if you look at here also, right, the deserializer output is actually there are some kind of signals on top of this main clock, the data signal, and this is basically coming from the clock coupling. So then this coupling also we can reduce by some mechanism. Clock data recovery, I already talked about it, and for further I think we can refer to, there are multiple references available, we can go through it. Clock generation circuit, again PLL is generally we used across the board to do this the clock phase alignment, the clock generation. There are obviously multiple ways to implement the PLL, right, and the main challenge today is getting a low power, low area solution for the PLL, right. So for high speed PLL, where we use LC based PLL for better linearity, LC means the inductor, it takes a bigger area and it has its own limitation to do proper modeling. So those are the challenges that we face, and then we handle those challenges, right. So for students and researchers, right, can look at all these challenges like creating a better PLL, right, creating a better power versus trade-offs kind of analysis of the PLL. You can look at what kind of PLLs are getting targeted for 224 gigabits per second Serdes and 112 gigabits per second Serdes, and then look at what are the challenges that we are seeing now, and how those challenges can be mitigated, right. Maybe you can perform this using some mathematical modeling, using MATLAB or any other tools which are available, or you can do some kind of analysis using models and simulations, and definitely that will be much useful for you. So this is one component where I think a lot of scope is still there. Equalizer, again this is one of the thing, again a very promising component that we use in Serdes as an equalization. Equalization is done, there are multiple reasons to do equalization. One reason is which is more predominant is equalizing the channel loss, because the channel has its own loss which is frequency dependent, right. So once you get the signal at the receiver, it is actually attenuated. So you want to make up for the loss, and then how you do that using some equalization technique. There are feed forward equalization technique, there are feedback equalization technique in transmitter and in receiver, and there are several other techniques through which we do precursor, postcursor mechanism, and then try to take the energy, distribute the energy throughout the entire duration, and then make sure the energy is not getting coupled to the other bits, right? One bit energy due to the channel channel attenuation, right? Channel's impulse response attenuation, right? It is not getting overcrowded to the next bit, right? So there are some kind of attenuation techniques, and here is again another big open area where people are still working, doing some research in terms of coming up with a better equalization techniques, right? And there is a huge scope. Marks and demarks, this is again pretty much, we talk about, there are multiple ways also to do. I'll not go in details of these marks and demarks. I will leave it to your personal interest to go through it. Okay, now emerging trends, right? Let's quickly look at the emerging trends, like, where we are going. We already talked about all those, like PAM4 or 224 gigabits per second kind of Serdes, which is let's say in PCIe Gen 6 and beyond, right? PCIe Gen 7 and beyond, right? And then we are also nowadays we are talking about chiplets. Chiplets is another technique where we do the communication from one chip to another chip, one die to another die, right? It's like it can be through a PCB, but again, that's a different standard protocol, right? And which is nothing but UCIe, Universal Chiplet Interface Express. So there also we talk about very high speed data communication, right? So that's one of the challenge, one of the technology which we are investing a lot in terms of chiplet, right? In this particular plot, if you look at it, it's like showing the actual bandwidth versus the IO bandwidth, right? So the IO bandwidth actually it doubles every 3 years, right? And we are in 2025. It's talked about like 256 gigabits per second, right? Whereas this actual bandwidth is a bit less, right? So actual bandwidth probably in the year of 2025, it's actually like around 512 gigabits per second, right? So this is the IO bandwidth and the actual bandwidth. I beg your pardon. So IO bandwidth is much lesser than the actual bandwidth. Okay, so that's the challenge that we are actually facing every day. Although the actual bandwidth we have to attain 512, but we are restricted by the IO bandwidth, right? So so this is the progression that we have, and then PAM4 signaling is another one, right? So as we move on from the speed, the IO bandwidth is not that helping us. So what we are doing is we are instead of having this amplitude from this big, right, we are distributing the amplitude in a 4 different level, right? So this way we are able to deliver the data in a high speed, but obviously there are some catch over it, right? Like here, if you see that you have from one level to another level, and here the one level to another level, the height is higher but the height is lower. So we need to make sure that the signal versus noise, right, signal to noise ratio is very stringent here, whereas signal to noise ratio is very high here. So then although PAM4 gives us a flexibility to transfer higher speed data, but we need to also make sure that we are taking care of the signal to noise ratio properly. So there are ways to handle. There is a big research going on this line. People are investing a lot to come up with better PAM4 signaling, better throughput. There are companies across the globe reporting every day a new benchmark number in terms of all these high-end Serdes. Yeah, so now if you look at it, I think some part of it we already discussed, right? Emerging trends. Process wise, from 1960s to 2020 and going on, we have seen process. So this process is semiconductor manufacturing process. So we started, we have seen it started with 75 micrometer process in 1958. I think it's like too early. None of us were born at that point of time. Probably right? And then 1958 to 1971, right? It's like there is a progression of the process technology advancements. 10 micrometer, Intel introduced, and IBM introduced 1981 1.5, and then 1995 internal commercial use of the process at 0.35 and 350 nanometer in 1990s, and 90 maybe we were in the schools that time, so that there the VLSI was getting introduced very that point of time. This is like internet commercial usage. This is basically the milestone and usage basically. Now in 2000s 2007 time frame, we talked about smartphone that got introduced, iPhone and Android 65 nanometer, 16 nanometer 2016, when we are talking about processors and a higher quality AI processors mainly. Then AI is again that time it got introduced, and then 2019 5G and deploy in 2090, and then 5 nanometer, 3 nanometer, 2 nanometer. Right now in the industry, the focus is on all those technology nodes at the lower, I mean around 2 nanometer, 3 nanometer, 5, 7, 16, all those nanometer technologies we are right now designing. And in terms of major products, the progression wise, like consumer electronics, PC internet, smartphone, and then now we are talking about AI and IoT, where we are dealing with high speed and high set of data, high volume of data, right? And then speed wise, as we see today, we are moving to 112 gigs to 224 and then 400 gigabits per second, and that will continue to evolve as we move on, right? Maybe 2030, 2050, I have no projection as such, but maybe someone who is more interested can look at, there may be some projection already made for 2050. Yeah, role of Serdes in neuromorphic computing. I just wanted to make sure, I just wanted to mention it, that neuromorphic computing is basically, the way human brain works, right? And then there is a huge demand and huge research that is happening in this area, and there are need of Serdes obviously there. And what kind of Serdes and what Serdes is getting used, that's a field where we can invest, we can definitely study further and look at it. And then second one would be in terms of quantum communication, right? Again, quantum communication is one field, let's say big data, AI, and there are many other components, right? So all those things, right? Robotics is coming into the field, and where neuromorphic computing is one of the factor, right? One of the research area. So all this, right? All this like quantum computing or neuromorphic computation is big data, and big data transfer requirement is there. You need to do a quick analysis of data, of huge data into a very quick time, and that needs a high speed processor, high speed data communication. So the interface needs to support it, and we need to be very accurate in terms of the interface, right? So so that is the main challenge, right? So how to handle this high speed and how to take care of all the errors that are coming because of the high speed communication, right? There are multiple factors we talked about today, and how we are taking care of them, right? So by considering all of this, right, in summary, innovative approaches to signal processing and modulation technique is definitely is the main focus today. Balancing power and performance, this is again on a kind of like a trade-off is applicable everywhere for the speed and reliability. Innovative packaging and thermal management solutions, that is another field that people are now focusing on. Ensuring signal integrity, signal degradation, crosstalks, avoiding all of them. How to minimize them, right? We know that there are issues, how to minimize. Scalability and future technology. I'll just take, but let me complete this summary. I know there is a question. Just give me 1 minute. I'll just quickly complete this one. Scalability for future technology. Quantum and neuromorphic system requires for forward thinking and adaptability and reduce latency, right? This is essential for applications like high frequency trading and autonomous vehicles, right? This is the focus on Serdes mainly for high-speed interfaces, and then we can actually look at all those lines. Yeah, proceed please.
Hi sir, good morning sir.
Yeah, morning.
Suggest me some topics on high-speed interface for technical round in interviews.
Okay, that's good. I can definitely share with you. So when we go to, let's say, interview, right, on high-speed interface, right, it depends on your exposure. Let's say, have you done some work on this high-speed interface? Have you covered any coursework, or have you done any kind of project? Let's say you have designed some module of a PLL, right? So the question of that interview will be on that particular line, and definitely the interviewers will ask the PLL you designed, right, for which application you have designed, right, and that gives a better perspective that okay, you have a better overall idea where the PLL is used and what are the critical factors for the PLL that you want to achieve. What is the glitch, the jitters, right? Sorry, not glitch, but the jitter numbers, right, that you are targeting for which application, right? So let's say in that way you can think of it, right? Let's say, I mean, interviewers can ask any question. It's such a vast field, right? It can be anything, but it depends on your interest. If something is there in your resume on this particular line, the questions will be on this particular line, means on the Serdes particular domain, right? The questions will be related to that only, right? You can also work on a synchronizer design, right? So synchronizer is pretty much needed, or you can design on a CDR, right? There are multiple components in the CDR. You can also design your project can be on a AFE, right, which is analog front end, analog feed forward equalization, right, for the receiver. So there are multiple components. There are inductors usage in the AFE for peaking and all, right. So you can replace the inductor with an active device, right. That's actually area saving, right. So in that way you can show some kind of advancement, right, some kind of benefits that from some available design to your proposed design. So then the questions on the interview will be on that line, right? It will not be any other thing, right? So to answer your question, I mean, what you said, like you are appearing in an interview and you want to prepare for Serdes, right? So you need to concentrate on some specific domain, specific block, right? And then understand where the block is used, why the block is used, what are the multiple parameters for the blocks that will be related to the overall Serdes, and then do some work there and then go to the interview. Right. So this is the final touch in today's discussion. It's like in the realm of advanced electronics, every circuit you design, every challenge you overcome brings you to one step closer to the shaping the world for tomorrow. So this is basically a tagline that you can use. So what I can tell, I mean, I may be going back to my previous answer that I have given you, is that there is a huge opportunity in this particular line and creating skill set for Serdes design. That skill set can be in terms of digital skill set, maybe digital means there are multiple RTL design or maybe digital verification, or maybe there are some other techniques that is used in Serdes, right, like modeling and analog techniques also, where we talked about it, right, like PLL or AFE or transmitter or any other components in the clocking. Yeah, so another thing could be the clocking, right? Again, clocking is a vast topic here. Clocking means like the clock structure, the clock, you have a clock and the clock is distributed throughout your transmitter or your receiver, which is like which takes a certain area, right? So that clock will has to travel, the clock has to travel that particular distance, right? And then from one place to another place, right, we need to make sure the clock edges are in sync, right? We cannot obviously there will be delay, there will be some kind of skews, between the clocks, and then we have to make sure that the data that is getting synced with the clock, right, is taking care of the skews, right. So that's a big challenge. It's a huge challenge that we are facing when we are going from speed, right, from low speed to high speed. So as a whole, right, Serdes itself is a huge ocean. We definitely the idea is to share some high level understanding, very niche understanding. Although it's not possible in 1 hour or 2 hours to cover them, or maybe it takes hours and hours to cover, right. So there are huge amount of materials available also. So my suggestion for the student community or for the researcher would be to look at to figure out very niche fields, right, very targeted problem statement, and work on that problem statement, right, and then see if you can come up with something. I think we are done for today. Thanks everyone. Thanks for your time and attention. I hope this is useful, the discussion is useful, and for further reading, please go through multiple materials available in the internet or any other place that you see, maybe your textbooks or any other places. Yeah, and the final, the last suggestion would be, if you are interested in this line, I would request you to do some projects, do some internships on this particular topic, and create some kind of skill set and grow your skill set in this line. There is a huge demand of having an efficient Serdes designer in the industry, and this demand will keep on growing. Thanks everyone. If there is no other call, we can conclude. Thank you. Thanks.